So I'm going to be talking about using functional programming in not quite object-oriented programming, but more imperative programming, which object-oriented programming falls under. So first, let's just define what functional programming is. There we go. So functional programming has a few core ideas behind it that drive it. The first is immutability. So this is the idea that data is never actually changed. We only create new data from old data while still keeping that old data. This has some safety benefits. So we know if we have some data at the beginning of our file and we go 1,000 lines down, we know that data is exactly the same as it was before, and we can work with it with that guarantee. The other one is the idea of pure functions. So a pure function in the technical definition has one input and one output. So if you think from the mathematical sense, this is something like f of x equals y. X is the single input, y is the single output. And having no output doesn't make sense, and having no input doesn't make sense there in order for it to be a function. The other idea that is more important in this case is that functions shouldn't have any side effects. So what is a side effect? A side effect is a changing of the state outside of the scope of the function. So, for example, a method in an object might have side effects in that it changes the state of the object surrounding it, and that is outside of the scope of the function itself. And this is why there's such a big clash between object-oriented programming and functional programming. Then finally, there's the idea of first-class functions. Now, this sounds quite odd, but it's just the simple idea that functions should be able to be used anywhere any other value can be used. So I'm just going to show that in the next slide. So for example, over here, we have the normal way we would usually write a function. Function add1, return x plus 1. It's very simple. And I'm using JavaScript for all of my examples here, but most languages do have the same functionality. And then we have add1 here, which is equal to a function expression. So we would then be able to call add1 with any number and return that number plus 1. Then just for modern JavaScript, we have this over here, which is just a more succinct version of this. They're functionally the same. And so just to, again, prove that functions are values, we can now move this function around. So we can move add1 into a variable called myFunction, and then call myFunction, and it'll have the same functionality as add1. So we can call myFunction as many times as we want, and we can call add1 as many times as we want. So now that that's out of the way, I'm going to talk, and then also just to kind of hammer the point that functions are values is we can have an array of functions, and this is going to be very, very important later on in this talk. Now, the main part of this talk is going to be talking about reduce operations. Now, reduce is a functional term, but we actually do reducing a lot in normal programming. And the example I want to show here is that of getting a sum of a bunch of values. So let's say we have the values 1 through to 5, and we want to start off with some initial value 0 because the sum starts at 0. So we can work with two numbers at a time, reduce those to a single value, and then eventually work all of these numbers down into one value. So we get 0 plus 1, that's 1, and then we use this 1 in the next calculation. So we take 1 plus 2, 3, 3 plus 3, 6, and so on until we finally get to 15, which would be the sum of 1 through to 5. So let's see the code of how we would do this imperatively. So normally, we would have an array of numbers, 1, 2, 3, 4, and 5. We then have our function reduce, and we pass in some collection to that, into that. We start at 0, we iterate over our collection, and we add each item to our result, and we carry that result over until we finally return it. And then here, if we just say reduce with these numbers, we would get the same result as here using the same process, just working two numbers at a time, working with this result and our item. So this is cool, but now let's try and start making this a little bit more generic, adding in a few functions and functional concepts. So first of all, one very clear idea we can see is that this is a reduce operation. It's not just a sum operation. So we have some hard-coded functionality here. Let's change that very slightly in this next slide by adding our add numbers function. So this is just very simply taking two numbers and adding them together. And we just substitute this in here. So now, for example, if we wanted to change this reduce to do multiply numbers to get our product of the whole collection, we could then just put multiply numbers in here. But we still have, we'd still have some duplication. For example, if we want our reduce to add numbers and also another reduce that multiplies numbers, we would have to copy paste this, and we don't want to repeat ourselves. So let's go to the next functional concept in here, and that's passing in an operation to be performed. So this is very core, and making this leap and knowing to do this is extremely powerful. So now our reduce is actually extremely generic. We can perform any operation that can take two arguments and return one value back, preferably, and then reduce that down to a single result. So for example, if we call reduce with numbers and our add numbers now, we're going to get the sum, but we can now reuse this with any function that has the same type of signature. So we go to the next slide, and you can see it works exactly the same with add numbers and with multiply numbers. And you see here, we would get 15 in this result. Now, this just highlights one simple problem with our current function, and that is if we do multiply numbers, we're not actually going to get the product of all these numbers because we're starting at 0, we're just going to get 0. So it's not very useful. Let's just take that one little step further and add some common sense, and we pass in an initial value as well. So now, when we add our numbers, we want to get the sum, we start at 0. That'll give us 15. Whereas when we multiply our numbers, we want to start at 1, so we get 120 as our final result here. Now, this is extremely generic, and you can see how this reduce could be used in so many places with any operation, as long as it takes in two values and returns a single value, can then be reduced. Now, I've kind of wasted our time here talking about this or talking about the implementation of this, because this is already provided in the JavaScript standard library. And we can see over here that this is exactly what we have. We have our function over here, and we have the standard library way of doing it over here. So this actually has it on the array prototype. So instead of passing in numbers, you say numbers dot reduce. Still put in your operation, still put in your initial value. This works exactly the same. This function is exactly the same as this whole imperative operation here. And we don't actually really care about the implementation details of this. We know it works, and it's part of the library, it's been accepted. And so there are many other functions like this, especially in the JavaScript standard library. Filter, map, a few others I'm sure I'm not really mentioning, reduce, write. It just does the same reduce operation, just the opposite way around. But all of these are extremely powerful and use the same concept of passing in functions to functions. And the technical definition for that is higher order functions. So a higher order function is a function that takes in another function as one of its arguments. And hopefully from this, you can see the power of this paradigm and how this can hopefully improve code, make it more generic and more concise. Now, so that's the first core part of the talk I want to talk about. Now I'm going to get a little bit more into the functional world and go a little bit crazy with functions. So let's look at applied functional programming. Now apply, this function here, is actually very important in traditional functional programming. And it's actually very simple. It takes in a value, x, takes in a function f, and it just returns x applied to f, so x taken as an argument to f. Now, why would we want to do this? It's not so clear now, but you can just see how we can use it. We apply 10 to add 1, and then this would hopefully return 11. Now, if you look at the signature here, I mentioned anything can be a reducing operation if it takes in 2 arguments and returns a single argument or a single value back. So what happens if we have an array of functions? Well, we can see if we reduce this array of functions with apply and take in an initial value of 10, we can see the chain of how this will work here. So we take 10, we apply it to add 1, and we get 11 as a result. We take 11, we apply it to add 1, we get 12 as a result. 12 applied to add 2 gives us 14, and then 14 applied to mul2 gives us 28. And this is exactly the same process as before, except now instead of adding numbers together or multiplying numbers together, we're just applying a value to a function. And you can see how this has essentially created a pipeline of processing for this number 10. And that is an extremely powerful idea because we don't only have to work with numbers, we can work with any values we want and any functions we want technically. So this is extremely powerful, but this is still quite an awkward way to write it. You know, we're saying functions dot reduce and then apply and then 10. You know, someone doesn't quite know what apply is doing. They're going to have to look into that. You don't know very clearly what these functions are. This might be defined 1,000 lines up. You don't really know. You have to go look it up. So if we want to make this a bit more concise, we're going to have to make a new function. And in functional programming, this is called piping. So you pipe a value into a function, and you pipe that result into another function, and so on. And you go through your pipeline, so it's called. So we can define pipe as a function that can take in an arbitrary number of functions. So we don't need an array anymore. This REST operator collates all of the arguments into an array that we can then use. And then this function is going to be returning a function. And this is a little bit confusing, but remember, functions are values, and so they can be returned from other functions. It makes sense when you think about this as a universal rule. And so then it will return a function that takes in an x and then does exactly this operation from before, reducing with apply with the initial value x. So we change our code a little bit, and now we have pipe, add 1, our add 2, and our mul2. Remember, this pipe is returning a function, so then we can make another call after it with our value. So we take 10, we add 1 to it, it's 11, add 1, 12, add 2, 14, and then times 2 for 28. And in this case, because we're taking in and we're returning the same value or same type every single time in this chain, we can change the order of this completely. We'll get a different result. For example, if we put times 2 at the top, we're going to get a completely different result, whereas any other way might get us something else. But this is fine because this allows us to become more flexible in our code and more flexible in the way we process this data. So on the next slide, it's essentially pipes all the way down if you want to get a little bit crazy with it. So let's say, for example, we have a pipe where we want to fetch our data. And let's say every time we get our data from some kind of data source, like a NoSQL database or anything like that, we want to clean it. So we get it and then we clean it. That's what this pipe will be doing. Note it hasn't been called yet, so it is still a function we can use and pass around because pipe returns a function that can be called. And let's say we have get metrics. And let's say whenever we want to get metrics from some piece of data, we want to pre-process that data and then extract the information. And then we can put those two pipes together. Pipes are functions, so we can pipe them together. So we can then fetch data and then get metrics. And what this will do, if we go into the pipes themselves, it will get the data, clean the data, then pre-process the data, and then extract information. And these pipes can be changed around, the order can be changed. Let's say after we pre-process the data, we have some other function we need to perform. We do this before we extract the information. Maybe we don't even need to pre-process the data anymore, we just remove that. So this is an extremely flexible way of writing code. And it's also very clear. you can clearly see from this final process, we want to fetch data and then get our metrics. That's all we want to do. We don't care about the implementation when we're looking at what our code is doing. If we need to look at the implementation in terms of bug fixing or anything like that to try and understand the code a bit more, we can go into these functions. So we go into fetch data and we realize what it's doing. And then we might want to get into get data to realize what it is doing. And if we want to actually run this process, we might call final process with some kind of connection string, which is what get data would start with. And then that would get passed down, turned into data, and then it would get pre-processed or turn into pre-processed data, and then finally be extracted to the actual metrics. And you see here that we're not actually destroying any of this data as we're processing it. We're just creating new data from that old data. And a very good analogy for this, if it's still a little bit confusing, is sound processing. So for example, here, this is from just some sound editing software. We would have a parametric equalizer, then a compressor, then take it through reverb, and then whatever that is. And if we change the order of this, because a sound signal goes in as a sound signal, gets processed, comes out as a sound signal, this order can be in any order, but it will change the actual resulting sound wave that gets produced. So this is a very different way of writing code. It has its own challenges, but I believe it's extremely powerful. And I hope at the very least, we can see how using functions and higher order functions can make our code much better. Thank you.